Hello, everybody. Thank you for being here today. In our webinar today, we will take a glance on electrical power analysis, and according to them, try to define what makes an instrument a power analyzer. Afterwards, we will take a look at the audience and applications of power analyzers, and finally discuss the challenges in power measurements and what can both manufacturers and users do to overcome them. Before we start, I would like to shortly introduce myself and our company. I'm Stelios Dimakis. I'm Sales and Application Engineer by Zimmer Electronic Systems. Our company, Zimmer, is a medium-sized company of 60 people. We are based near Frankfurt, Germany, and our area of expertise is power analysis. So we design and produce exclusively power analyzers for the past 40 years. We will start with the fundamentals. We will try to answer what makes an instrument a power analyzer. There are different ways to describe a power analyzer, and it always comes down to power measurement. So a power analyzer in principle is an instrument that measures power, but does that with very high accuracy and bandwidth. This high accuracy and bandwidth enables not only the very precise measurement, but also deeper analysis on the measured power. Here we see on the slide a part of the measurements that a power analyzer can perform. And these are fundamental properties of power analysis. Now, taking a closer look in the formulas, we can see how certain defining requirements for a power analyzer can be derived from them. Let's, for example, take a look at the active power. Here we notice two things happening, one of them being multiplication and the second being integration. Integration, first of all, requires sampling. And the higher the sampling rate, obviously, the more accurate the result of the integration will be. So a high sample rate is a requirement for power analyzers, which also enables them to measure signals of high bandwidth. Moreover, the starting and ending timestamps of the integration period, we see them here, T1 and T1 plus T, they must be recorded accurately for the calculation to be as close to as possible to the real measured value. So a solid time base is a key requirement in power analysis. In periodic signals, an integration cycle must include an integer multiple of the signal's period. So here, besides the precise time base, a reliable detection of the zero crossings plays a key role. The power analyzer, finally, must be flexible in adjusting the durations of these cycles in order to deliver measurements with no gaps. The second key component of the formula of active power is multiplication. Doing the multiplication, of course, in theory is simple, but in practice there is an important factor that comes in play, and this is synchronicity. In other words, the voltage and current samples that are being multiplied here need to have been recorded at exactly the same time for the resulting power to make any sense. In design, that means that the current and voltage signal paths need to be, if possible, identical, since even some millimeters of conductor can introduce nanosecond delays that will harm the synchronicity of you and I. Design also needs to consider the effects of all connections that may increase impedance on the signal path even slightly and cause unwanted phase shift on one of the signals. The best practice in order to come to the best possible synchronicity is to use internal shunts and channels of voltage and current that are integrated into the same power measurement module. This differentiates power analyzers from other instruments that, for example, only have voltage signal inputs and rely on external sensors for the measurement of current. Of course, even when the above apply, the measurement in the end can only be correct if the actual values of the voltage and the current signals are correct. So here we are talking about measurement accuracy, and this is why precision power analyzers have a very tight specifications on their measurement uncertainty. Measuring the power, as explained right now, together with determining the RMS values of voltage and current, basically lets us calculate most of the electrical properties that we see in this slide. These characteristics that I mentioned before, paired with high computing power, will additionally enable the power analyzer to perform further analysis on the transient on power such as star delta conversions or the recording of transient states, harmonic analysis, which itself will give further parameters such as phase angle, vector diagrams, THD, distortion power, and more. Finally, when talking about systems and efficiency, a power analyzer must be able to allow a logical grouping of its input signals to which the user can then apply specific settings like filters and consider them as separate entities on their system, for example, inputs and outputs of different stages. This makes the calculation of power losses and efficiency possible. To conclude and summarize, a power analyzer is an instrument with integrated current and voltage inputs, high sampling rate, careful channel design, and high computing power that enable it to measure and analyze broadband power with very high accuracy on electrical circuits and systems. Now let's explain the necessity of power analysis and which industries and applications benefit from the use of power analyzers. First, let's try to answer the question, who needs a power analyzer and why? In short, everybody who cannot afford to waste power. In that sense, the user of a power analyzer does not want to simply know the power that they are getting as much as they want to know the power that they are losing. That makes the power analyzer an ideal instrument for test and R&D engineers who want to evaluate losses and efficiency with very high accuracy. The point is to track exactly where and by how much a system's input is not being utilized and what one can do to improve its efficiency. So when does it matter most? It comes down to those power losses that have a significant impact on a system, no matter how low they may be. Some losses, for example, cost money. Let's say an efficient renewable energy generation plant will not only produce cheaper power, but possibly also have shorter investment payback time. So it makes sense that investors prefer the most efficient solutions and manufacturers strive to make their products as efficient as possible. Other losses can limit the usefulness of a product. Think at electric cars, for example, and how the range of a vehicle is affected when its powertrain is not designed to perform at its best. There you have several stages of often a bidirectional power conversion, and each one takes its toll on efficiency. So when powertrain engineers struggle to gradually improve the efficiency of each stage percent by percent, they need a measuring instrument that can verify these small but important changes. Then we need to consider that losses in most cases are expressed as heat, which in turn means that they cause long-term wear on components and reduce their lifetime. So the durability of a product depends heavily on its efficiency. And finally, we must, of course, not forget that energy is a scarce resource and we are all working for a sustainable future. So minimizing energy losses is a high priority in many industries. Let's now take a look at the most important industries that power analyzers serve. It's a very broad market, but we will go through the most common segments. So, first of all, we have applications of power analyzers in all power electronic devices. Power electronics are everywhere, from USB chargers and power supply units to electric vehicles and wind farms. For example, let's take power supply units. There are different types of losses to be evaluated there, namely conduction and switching losses, which can be supported by harmonic analysis to fully understand the behavior in such systems. A power analyzer is the right tool for that. Power analyzers can also be used to measure magnetic core losses on magnetic elements, such as chokes or power electronic converters, by measuring the power resulting from an excitation current to the core and the induced voltage on an open circuit setup. Through further clever testing, one can even calculate the magnetic flux and magnetic field strength, and thus draw point by point the BH curve of a magnetic element. In the lighting industry, we have power analyzers being used for LED driver efficiency, ripple factors, and power factor measurements. Moving on now to a very hot topic, which is electromobility. Here we separate the application areas to those related to the powertrain, to charging stations, and to batteries. Let's start with electrical vehicle powertrains. An electric vehicle consists of several mechanical and electrical powertrain components, such as motors, inverters, DC-DC converters, etc. And the synchronous and real-time evaluation of the efficiency of each power conversion stage and of the entire systems require a multi-channel power analyzer. Also on EV powertrains, we see often regenerative braking. Both electric and hybrid vehicles use this method to utilize the energy which is returned from the wheels to the motor during braking to charge the battery or provide quick acceleration, which is especially useful in racing applications. Here, power analyzers allow powertrain engineers to monitor the bidirectional power flow between wheels and battery and assist them in designing efficient regenerative systems. Another system of the EV's chassis is an onboard charger, and it is not only power and losses to be measured there, but also the charging voltage and current. Now, in EV charging stations, we use the need for power analyzers in several stages. First of all, we have the verification of the product itself, so the efficiency of the charger and its voltage quality on the output side. Fast DC chargers, in addition, include, besides the rectifier, an additional DC to DC conversion stage to control the charging current. If necessary, such systems also use a high-frequency transformer to achieve galvanic isolation. So here we see again several stages of power losses which require measurement, as well as voltage and current parameters. Apart from that, EV charging stations contain energy meters. The accuracy of those energy meters affect directly their users, who are billed according to the measured energy. To ensure trust between provider and consumer, local authorities as well as the European Union dictate certain examination tests for the certification of each charging station. These tests require the verification of the accuracy of the complete charging process by comparing the energy metered at each charging port with the energy measured by a reference instrument, that being a power analyzer. So both charging station manufacturers and certifying institutions can integrate power analyzers into their compliance test benches. On the grid side, charging stations or wall boxes must be compliant with the grid, In other words, they should not disturb the grid's voltage and frequency. So there we also use power analyzers to verify that. Finally, in electric vehicle batteries, or batteries in general, in fact, we can also say, a power analyzer helps monitor charging cycles and measure some basic electrical properties such as charging voltage and current, energy capacity in watt hours, and charge in ampere hours, as well as internal resistance and thermal joule dissipation, and many more. Power analyzers often offer the possibility of external control of other instruments. For example, internal commands can trigger relays in the charging circuit. This means that the charging cycle can also be controlled by other user inputs or automatic controls running on the power analyzer. Let's move to the next slide. Here we have renewable energy applications. And of course, you know that renewable energy installations include power electronic converters to control either the supplied power to the grid or stabilize voltage or store any excess energy for later use. So power analyzer applications here also include all typical measurements on power electronics. Taking a look at them segment by segment, we see that in solar energy, we have obviously solar inverters whose efficiency can be evaluated by a power analyzer. Solar inverters use a maximum power point tracking control algorithm to regulate the voltage and current from the PV panel. In practice, the points of maximum power can be verified and mapped by real measurements using a power analyzer. At the same time, one can monitor the power factor, total harmonic distortion, active and reactive power of a PV plant. Same principles, of course, apply to wind turbines, as power converters are also used there. Although the maximum power point tracking has traditionally been used on photovoltaic power, it has been recently applied also to wind turbines, where the goal there is to load the wind turbine just right so it delivers the most energy at any wind speed. The role of a power analyzer here is the same, creating an efficiency map for different maximum power points, and furthermore, one can use power analyzers to verify the quality on the point of common coupling with the transmission grid. Water electrolysis system require precise and well-controlled power supplying equipment for safety and optimal efficiency. We have in the electrolyte cell current harmonics that can cause additional losses. So here, power analyzers can be used not only for the typical measurement of system losses, efficiency, and harmonics, but also as monitors of kiloampere currents. Moving on now to further segments, we commonly see power analyzers used for the measurement of short circuit impedance and load losses on transformers, as well as magnetic losses. The method for the measurement of magnetic losses here is identical as what we mentioned in power electronic magnetic components, but on much lower frequencies. By measuring losses, we can determine then the transformer's overall efficiency, and having in hand several other electrical parameters, we can verify transformer design according to the specifications of the IEC 60076 standard. When it comes to conformity, testing there is when it comes to conformity tests, I mean there's a lot that the power analyzer can do in that area, and especially on electromagnetic compatibility and CE compliance. For example, one can carry out tests for harmonic emissions and flicker on household devices, or measure low and standby power modes. Another point about conformity, which I could also have mentioned earlier with renewable energies, is the newly introduced standard, which describes requirements for the harmonics being produced by the inverter of electrical energy supplying equipment on the low voltage grid. This, for example, concerns manufacturers of low power solar inverters that need to certify their products according to the EN 61000-3-16 standard in order for them to be able to be used in Europe. There are many more applications. There are many more applications such as aerospace and defense, but I'm going to conclude with something more everyday and common, and this is digital energy meters. We mentioned them earlier due to their use in EV charging stations, but energy meters are used in the entire electrical network for measuring household consumption to renewable plant generation. In all cases, as soon as the meter readings become the basis for billing, the base for billing, the consumers have vested interest in the DC meters reliability and precision. So here local authorities take the role of the supervisor between energy supplier and consumer. For example, in Germany, we have the Eichrecht law, which dictates that all components involved in the collection and processing of energy must operate in a trustworthy and transparent way. Similar laws most likely apply in Italy and most other countries, and their precision power analyzers are being used in the development, verification, and calibration stages of such devices to ensure their accuracy and compliance. Moreover, since these energy meters use repeating pulses to indicate the consumed energy, a power analyzer being able to analyze these pulses can serve in examining their stability and consistency. Okay, so now having seen the most common applications, let's take a look now at what are the challenges when measuring power. We have an interesting variety of challenges in power measurement, and the solutions of those rely both on the manufacturer of a power analyzer, but also heavily on the user. So let's take a look at them. As I mentioned in the beginning, accuracy is key in power analysis, and measurement uncertainty is, of course, an issue. So achieving the best accuracy requires a high precision instrument whose measurement uncertainty can be traceably calibrated. At the same time, the manufacturer should provide clear and comprehensible specifications. The uncertainty is in most cases specified as a percentage of the measured value plus a percentage of the maximum peak value of the applied measurement range. A clearly specified instrument makes it easy for its user to calculate the uncertainty of their measurement under all circumstances. In other words, the fewer external parameters affecting these formulas that we see on the table here, the better. For example, in the specifications here, we see that the uncertainty is specified independently from the power factor. The user from their side must ensure that they are getting the most out of their instrument by operating the power analyzer under specified conditions. For example, in proper ambient temperature and after proper warm-up, and calibrate their power analyzer at regular intervals. The longer the manufacturer can guarantee that their specifications remain valid after calibration, the easier and cheaper, of course, it is for the user to follow the appropriate calibration intervals. Interestingly challenging is the measurement of highly dynamic signals. To understand the challenge, we need to come back to the typical formula for measurement uncertainty that we also saw on the previous slide. You also see it here. Here we have a component of the error originating from the measured value and another from the applied measurement range. When we have short dynamic changes, like those happening within the measurement cycle, for example, spike on the signal during a period, the role of the range's crest factor is important. As crest factor of a range, we define its maximum peak value divided by its nominal value, this formula that we see here, and it's a common term in test and measuring instruments. To understand its significance, let's look at the AC voltage and current of a USB charger. The network voltage on the left is sinusoidal as it should be, while the current draw from the network, as we see on the right, follows this spiked pattern. On the left graph, the signal is around 230 volts RMS and has a peak value of 330 volts. So the proper rate to operate the instrument in this case is the one with a nominal value of 250 volts. As the peak voltage of the signal does not exceed the maximum peak voltage of the range. The crest factor here is 400 divided by 250, which gives 1.6. It's easy to understand that the higher the utilization of the range, in other words, the closer the signal's RMS is to the range's nominal value, the influence of the range component becomes less significant in the total measurement error. So here we would benefit from a low crest factor, so that the range component of the uncertainty can be as this one can be as low as possible. Now let's take a look at the current on the right. Here we have an RMS current of around 70 milliamps with a peak value of around 425 milliamps. If we are to select the appropriate range for this signal, or let the power analyzer select it automatically, we will be using the range of 150 milliamps, because this is the lowest range, whose peak value of 469 milliamps covers the signal's peak value. So even if there is the RMS, if the RMS current of 70 milliamps could be theoretically covered by the 80 milliamp range, so one step down, we wouldn't be able to use it because our signal would be clipped at the maximum value of the range, the 224 milliamps, and thus we would get a very high error. Anyway, this is the reason that we need to step up a range, which has a crest factor here of around 3. Here we can say that we somehow benefit from the high crest factor, because had it been lower, we would potentially need to step one more range up with possibly quite higher peak value and a likewise higher range error component. So my point is that range design is, from the manufacturer's side, a big challenge, and the careful selection of crest factor is important for the overall accuracy of the instrument in all ranges. Also, a low distance between the ranges is also beneficial. As we see here, the current ranges are progressing by a factor of 2, but there are instruments with factors of 3 or up to 5 between ranges. The customer, from their side, must ensure that they select the measurement ranges properly. Now, when it comes to long-term transitions, let's say those who take place over several measurement cycles, these are also not an easy issue to handle. A power analyzer should offer the choice for the user to either select the ranges manually or let the instrument automatically determine and apply the correct range. Using automatic range selection ensures that the appropriate range will be always applied to the measured signal, thus minimizing the range component. In the uncertainty, but it involves range transitions which may introduce gaps in the measurement. Therefore, a power analyzer must be able to handle automatic range transitions as quickly as possible, but in fact, this will there will be always cases where those are unavoidable. So we come to the other side, setting a range manually. When we manually select a range, we ensure the continuity of the measurement and the delivery of the cycle values without any gaps. But this can potentially lead to higher uncertainty in the measurement. For example, let's imagine a current which can go as high as 10 amps under heavy but only occasional load of the DUT, but the steady state current is 2 amps. Using the range of 10 amps to measure this will save us from range transitions, but will force the measurement of 2 amps to happen at a higher range with an unnecessarily high uncertainty due to that range component. So as we see, this is a compromise between continuity and accuracy, and it lies solely on the user, in that case, of the power analyzer to consider the advantages and disadvantages of manual versus automatic ranges and proceed according to their priorities. Moreover, the ability to analyze power in time and frequency domains simultaneously is another challenge. Such analysis is important for the real-time separation and evaluation of different types of losses on a complex system. For example, a motor drive. On Zimmer power analyzers, we use smart signal processing techniques like dual path, where we create 2 paths of the same signal and apply different filters and sampling to them. So we have a wide path that delivers unfiltered full band measurements of power, while a second narrow band path uses an anti-aliasing filter to ensure good FFT results and allows the user to apply further digital filters to isolate bandwidth of their signal that they wish to measure separately. This architecture allows the simultaneous measurement of 3 value groups, the wideband values, the filtered values, and the harmonics. Apart from that, like in every electrical measurement, we have the influence of noise, electromagnetic pollution, grounding issues, which can be solved by the manufacturer by offering filters for the power measurement, and on the design side by using isolated power supplies and differential measurement inputs. And the user from their side can minimize these issues by following best measurement practices, such as the use of good conducting and shielded leads, avoiding loops on the measuring cable layout, proper grounding, and by ensuring connection integrity. Moreover, we know that ideal measurement instruments are only theoretical. So in reality, volt and amp meters have resistances that are in contrast to ideal instruments, neither infinite nor zero. And this leads to always to a current leakage on the voltmeter and a voltage drop on the amp meter. This is why it is important for the user of a power analyzer to consider the effects of the placement of the volt and amp of the voltage and current channels on the measured circuit. The layouts shown here are known as voltage correct and current correct measurement, respectively, on the left and on the right, and need to be considered depending on the measurement. For example, measuring the standby current of the load here using a voltage correct measurement will result in a small voltage drop on the amp meter's internal resistance, Ri, and a small current leak on Ru. The measured current I is the sum of the load current that we want to actually measure and the leaked current into the voltmeter. Since both these currents are very low, we are measuring a standby current. The part of I caused the part of I caused by the leakage current into the voltmeter will be comparable to the real load current, and the error of the current measurement or of the overall power measurement will be significant. If we instead use the other topology, if you use a current correct placement, the leakage current on the voltmeter will play no effect on the measured current. The voltage measurement will be, however, affected, since the voltmeter here will see the source voltage, and not the real voltage on the load, which includes this small voltage drop on the ammeter. However, the effect of this small voltage drop to the total measured voltage will be much smaller, since the DQT's voltage is much higher. So in this case, it is worth opting for a small voltage error in order to avoid a more noticeable error in current, which would lead to a less accurate power measurement. Then we have power measurements in low power factors. These are especially tricky because there even minimal changes on the phase angle can lead to high deviations on the measured power. Therefore, the measurement of the phase angle must be as accurate as possible, and to ensure that, we must be able to record voltage and current signals with very precise synchronicity, as we mentioned in the beginning. This is achieved by careful analog and digital design, and is best guaranteed when the voltage and current channels are integrated into and bound into one single power measurement module. To further fine-tune the phase measurement, a power analyzer makes the delay time between voltage and current inputs adjustable. Now, often we need to handle voltages and currents voltages and currents that can span from milli to kilovolts and amps. Up to a point, this can be directly measured from the power analyzer. In those cases, the measurement channels need to be designed so that they can handle highly dynamic signals. We often see designs where different inputs are used for low currents, and to measure higher currents, a different current module needs to be installed. So these builds are impractical. On the other hand, a power analyzer must be able to handle signals on its entire range on a single module. Of course, every instrument with sensible dimensions has its limitations on its direct inputs. For higher amplitudes of currents and voltages, current sensors and voltage dividers are used very commonly. And although these introduce additional uncertainty to the measurement, sometimes they are necessary. In those cases, at least, the best compatibility with a variety of such sensors is crucial, as well as efforts from the manufacturer to make the connection with them as seamless as possible by designing the power analyzer to be able to recognize the type and divider ratio of the sensors, apply scaling and ranges automatically, and supply active sensors with power. Finally, the ultimate goal and challenge is to measure losses and efficiency, even in complex systems, such as this example with this two-level three-phase traction inverter. There are different states on these systems whose efficiency we want to measure. We want the losses on the DC converter, the inverter losses, we want the losses on the motor, and finally we want the total system losses. In other words, what part of the energy drawn from the battery is not converted, does not end up as mechanical energy on the motor's shaft. Its electrical states has quite different characteristics and needs to be handled differently. So we obviously cannot apply the same settings for filters, synchronization, and ranges to the entire instrument. But also, at the channel level, we must be able to get collective values from certain channel groups. For example, when we're measuring the power on the inverter output by using 3 power meters, but what we need is the sum of this power. Here is where the logical grouping of the physical inputs becomes crucial and enables the instrument to see the inputs of the different stages as individual entities. Now the inverter losses can be derived by simply subtracting the collective power of group 3 that represents the inverter output from the power of group 2 that represents the input to the inverter or the output of the DC converter. And that symbol, of course, is also the efficiency. Instead of subtracting, we are dividing the group powers. Having such groups makes it for the instrument possible to understand that there are different entities under measure and not just blind inputs. And for the user, applying settings according to the group and calculating losses becomes very simple. As for the non-electrical power, namely the mechanical power of the motor, this can be easily handled by analog and digital inputs that can read signals from RPM and torque sensors. This ultimately leads to a clear picture of the overall system efficiency. Now we will proceed with a live demonstration of a power measurement. We are using here a Zimmer power analyzer, a model 6 LNG671, and our test subject today is a USB wall charger. So I am connected here remotely with the LMG. I'm running the LMG remote software to operate the instrument from my computer. I believe you see that on your screen.
Yes.
And yeah, first of all, let's think about the measurement. What we have to measure. We have a device with an AC input and a DC output. So we need 2 channels for this measurement. And on this 6-channel device, I have grouped, I have placed basically channel 1 into group 1 and channel 2 into group 2. So channel 1 will represent my AC input. Okay, I think we have some, yeah, and group 2 will represent the DC output. Okay. So there we have our 2 groups, output, input. Let's take a look at the signals. I'm going to the scope graph, and I will place the voltage, current, and power on the AC side. Let's also split the signals so that they have a better view. Just a second. Yeah, there we see them. Okay, we see a pretty sinusoidal voltage as we expect. We see some spikes in the current, and we also see that yeah, the power is something in between. Okay, I should revert back to the original view. Okay, we see that here. Let's also take a look at the signals on the DC side. I then am now placing the voltage of group 2 and current and the power of group 2. Again, let's create a split overview. Okay. Yeah, we have pretty stable signals with expected ripple. Okay, so let's see how we can set up now those groups. If I go back to the group settings, I have, as you see here, some settings to apply to the entire group that represents my input. I will change it to dual path. I will also show the effects of dual path later. The settings, we don't have to do much here. We see we have good measurement of the frequency. It is around 50 hertz as we expect. And let's take a look at the DC output. Here we don't have measurement of the frequency because we have a DC signal, so we expect that initially, but we can take it a step further and try to measure the frequency of the ripple. Let's take the voltage ripple, for example. So I selecting the signal source for the synchronization being the first voltage of my group. You can see what kind of different options I have. I can set a level or a hysteresis. A level would help if I had an absolutely stable DC signal, but I will do something better. And instead of that, I will apply a high pass filter. 100 millihertz, it's fine, I think. Enter. Okay, maybe we have to adjust it a little bit. Oh, no. We see here now we have a frequency measurement. Of course, on the DC signal, this is the frequency of my voltages ripple. So we have that as well. Yeah, range selection is automatic at the moment. Yeah, let's take now a look at the measurements. On the LMG, we have the default menu. This gives us an overview of the basic properties of the measurement. I could also select to see more values if I want. So I have some basic voltage, some basic current properties, and then a summary of my power and of my frequency. We see we are charging at 5 volts. We are drawing, almost 700 milliamps of current. And on the AC side, everything is as expected. Network voltage, and yeah, we have we see the power factor here. What I can additionally do, and would be interesting on the AC side, would be to see the harmonic content of those measurements. So I can change the display to harmonics, and now I see a table also with an overview of the measured harmonics. I also see some further properties, some further measurements that derive from the FFT. I see the distortion power, the total harmonic distortion of the current, and several others. If I want now a more detailed picture of my current, I can go to the current menu. We'll switch back to the original view. And now I have here many more properties of the current. And likewise, I can do that, okay, for all groups, of course, and likewise, I can do it for the voltage. The most important thing here is, however, to see what is the power on the input and on the output, and compare them, calculate efficiency and losses very easily. So going to the power menu, again, similar structure. We can either display them as harmonics or as simple values, but the most interesting thing in this menu is the efficiency tab. And here I see, if I take the DC output, compare it to my AC input, this is directly the efficiency of my charger, which is 81% at the moment, and we have around 6 watts of losses. So it is as easy as that. And of course, having a more complex system using 3 or more groups, this efficiency table can be very useful to have a picture of the system in just one screen. Apart from that, going back to our graph, we can take a look at a plot. Let's me fit it once to see everything. So yeah, this is a long-term recording of voltage, current, and power. And if I disconnect my USB device, split again. Sorry, like that. Now we see directly the voltage rising, current dropping, and yeah. So this is okay. We have a weird voltage drop here, but let's connect again. The device, split again. Okay. In any case, this kind of plot serves if I want to observe a full charging cycle of a battery, then I can utilize this plot. I can also measure energy and charge and have them plotted, or measure them separately in the energy menu. In the energy menu, I have different triggers to start and stop the energy measurement, such as a manual start and stop, or I can make a schedule, or I can use external triggers to start and stop the energy measurement. So this is how it works. So I believe that you also find this kind of menu structure, this kind of display very comprehensible, that it feels like you can come to the value that you want to measure, that you want to see pretty quickly. So this is more or less the live demo for today. Before we finish, I would like also to show you the dual path concept. So let's take one signal. Let's take the power, okay, and take the voltage signal out and replace this signal. Again with the power in narrow band. So here I have two options. Because I have changed the signal processing to dual path, now I am measuring the same signal two times, filtered and unfiltered. So I will take the narrow band signal here. I will change the other one to wide band and see what happens. Let's, okay, we cannot see much here, but if I zoom in a little bit, yeah, okay, we already see here the presence of more distortion on the wideband signal, but I can also apply additional filters here and make it even smoother. So I could go, I'm in the wrong group, I see input, apply a low pass filter. Now we have a low pass filter at 15 kilohertz, which is set by default, but I can okay, no. I can set it custom to any other filter. I have the option of Betzel, Butterworth, or Cherbyshев filters. Let's just to see the difference, make it 500 hertz. Okay. Go back to the graph and see the effects. So I'm not interrupting the measurement. I'm not measuring one time with filter, one time without filter. I have the same measurement executed at the same time in both modes. And I also have it on the default menu. For example, I can always see the narrowband values and then see the wideband values. And if I want, I can also create custom menus where both of them are presented next to each other. I think we have covered the basics today. We have seen how a real power measurement takes place. There are, of course, many more things and many more applications where we could go in depth, but I think this would be what we already discussed serves the purpose of today's webinar. So at that point, I would like to conclude and happily take your questions.
Perfetto, grazie Stergios. Speriamo di avervi offerto dei contenuti nuovi quest'oggi. siamo arrivati al termine del tempo per il webinar. Se avete qualche domanda potete attivare l'audio o scriverle nella chat, oppure potete comunque scriverci per email. Tra oggi e domani vi manderemo la mail di ringraziamento per la partecipazione, dove appunto ci sarà anche la registrazione del webinar. Ci sono domande? Beh, sì.
Buongiorno, io avrei
Ok,
una
perfetto.
domanda.
Prego.
In inglese la facciamo?
Se riesce, sì, se no la traduciamo.
No, riesco. Hello, this is Bruno Sintolesi from Hitachi Rail STS. So I would like to ask a couple of questions if possible. The first question is if this tools is able to provide a report compliant with the EN 5160 or IEEE 519.
Not directly. We have a software that can create reports, but the standards that we support are typical EMC harmonics and flicker standards for C compliance. So no, you cannot automatically create reports, but you can use possibly the power analyzer to get the values, export them into any format you want, and then use this measurement to create your own reports. But at the moment, there is not software that supports the standards that you have mentioned.
Okay, so basically you have to extract the raw data,
Yes.
and then you make the post-processing by your own.
Yes.
Okay.
Yeah, this is possible.
Yes, and second question is related to the probe that we can use in order to measure the current and the voltage, because in my experience, sometimes I have to measure on the medium voltage side in order to make the harmonic measurement according to the standard that I have already mentioned. So do you have some tools, some probe for suitable for that?
Yes, we have high voltage dividers up to almost 16 kilovolts. I don't know what your voltage level is at the medium voltage, but we can cover up to 16 kilovolts. We can cover it.
So in general, we are so on the medium voltage side, so we are measuring around 15, 20 kilovolt, but in general we connect the probe on the secondary side of the voltage transformer for the voltage, and on the secondary side of the current transformer for the current. So that's why in general, especially for the current, we have to purchase specific, high sensitivity current in order to measure on the secondary side of the CT. So I was wondering if you have something similar.
Okay, we do. I may show you our website here at the moment. And when it comes to sensors,
yes.
If you see that,
yes,
I will
see.
zoom out a little bit. So this HST, this is a precision wideband high voltage divider. So this is the device. So it's not a probe, something that you hold with your hand and measure something. It is a tabletop unit or a rack unit. It's not too, this is how it looks like. So we have BNC outputs on the low voltage side, and then we have, cables on the high voltage side, and we have different models, 1 up to 3 channels. The highest model, HST12, can go up to 16.8 kilovolts. So partially, And when it comes to current sensors, there we have a big variety. So if you want the highest precision, I would suggest the PCT. It has accuracy of 0.01%. They are great sensors, very compatible with an LMG, or even if we are not using one. I mean, they are very good sensors. But apart from that, we also have and other selections like current clamps, Hall sensors, and more. So there is I believe that you will find what you want pretty much, even on the very high currents. Very high, I mean, not just 1 kiloamps, but we also have some transformers that can go up to 10 kiloamps, for example.
Okay. Thank you very much. Thank you.
Thank you too.
So, Sergio, we have so first question, Paolo Piccardo, abbiamo risposto già alla sua domanda, se mi risponde, perché penso che volesse informazioni sulle sonde.
Sì, assolutamente. A un mio collega abbiamo chiesto la stessa cosa. Grazie mille. Siamo in ufficio insieme. Grazie a lei, Sara.
So
thank you very much.
Grazie mille. Another question, Sergio, is what happens to the voltage and the current synchronization when an external current clamp is used?
Yeah, there you naturally have some delay, and current clamps specified not only on their accuracy in terms of amplitude, they have also specifications on the maximum delay they can introduce. The good thing is that the power analyzer can adjust this delay. So there are settings in the on the power analyzer for the range and for the expected delay. So you can correct that if you know more or less what the time delay from your current clamp is.
Okay. The second question, I don't know if you need more information, is how does the LMG 671 work for charging, discharging of batteries, lithium-ion batteries? I guess he's talking about,
Yes, it depends on what do you want to measure. With a power analyzer, the best thing you can do, first of all, is measure the efficiency of the cycle. So record the cycle, using the plot graph that we saw before. Record the charging process, the discharging process, the energy, the charge drawn at those stages, the power, the quality of voltage, the quality of current provided to the battery. You can do that all with the power analyzer. And there's also for more advanced use, I may be able to show it here on the instrument. Imagine that you have a circuit that you build a test circuit for a charging cycle. You build a couple of relays which change your battery from charge to a discharge or to a standby mode, and you can even control these relays using inputs from the power analyzer. So, for example, we have here a general purpose input-output interface. These are all 5-volt inputs and outputs. So you can say, okay, if something happens, if I press a certain button, or you can even write a script and says, okay, if the voltage goes to that level and stays that for 5 minutes, then set the pin from 0 to 1 and the other pin from 1 to 0. In other words, switch my circuit, switch the start discharging and stop the charging circuit. So there are more things you can do besides the typical electrical measurements. You can also do more advanced testing on batteries. I hope this covers the question. If you wanted to ask something very specific.
Okay. Yes. All right. So at the moment, there are no other questions. Sergio, thank you very much for your time and also the opportunity you took to come over in Bologna. Io ringrazio tutti per la partecipazione e come sempre per il vostro tempo. Aspettate da Emanuela la mail di ringraziamento con tutte le informazioni. Ci sarà anche il link per i prossimi eventi, sempre gratuiti, che organizziamo, nel caso vogliate partecipare. Per ora vi ringrazio, vi saluto e vi auguro un buon pomeriggio. Arrivederci a tutti.
Arrivederci.
Grazie.
Arrivederci.